Imagine a flat, endless sheet of paper. To describe exactly where something is on it, we draw two number lines that cross at right angles right in the middle. The horizontal one is the x-axis, and the vertical one is the y-axis. They meet at a point we call the origin, which is 0 on both lines. Now any spot on the paper can be given a unique address, written as a pair of numbers in brackets. The first number tells you how far to walk across, left or right from the origin. The second number tells you how far to walk up or down. This whole setup is called the Cartesian plane, named after the mathematician René Descartes, who first had the idea of linking geometry and algebra this way. Why do we even bother with all these coordinates? Because the Cartesian plane is the bridge between shapes and numbers. A perfect circle drawn on the plane is no longer just a round line, it becomes an equation that describes every point on it. This lets us use algebra to study geometry. For calculus, this is absolutely essential. When we want to find the slope of a curve at a single point, or the area under a wiggly line, we first need to know exactly where that point is and how far it is from other points. The plane gives us a precise, numerical map of space, turning vague ideas about the steepness or area into problems we can solve with exact calculations. So, how do we measure the straight line distance between 2 points on this plane? The trick is to see it as the longest side of a right-angled triangle. Picture 2 points, A and B. Draw a horizontal line from A, and a vertical line from B, until they meet at a corner. The distance you want is the diagonal line connecting A and B, which is the hypotenuse of this triangle. The horizontal leg is just the difference in the x-coordinates, and the vertical leg is the difference in the y-coordinates. Now we can use the Pythagorean theorem. The square of the hypotenuse is the sum of the squares of the other two sides. So, the distance squared equals the x difference squared plus the y difference squared. Taking the square root gives us the distance formula. The order of subtraction doesn't matter because squaring makes it positive. Let's use this to solve a real problem. Imagine you're looking at a map, and your house is at the point 1, 2. Your friend's house is at 4, 6. What's the straight line distance between them? First, find the horizontal leg. The x-coordinates are 1 and 4. The difference is 4 minus 1, which is 3. Next, the vertical leg. The y-coordinates are 2 and 6. The difference is 6 minus 2, which is 4. We now have a right triangle with legs of 3 and 4. Square them to get 9 and 16. Add them to get 25. The square root of 25 is 5. So, the distance is exactly 5 units. This same method works for any 2 points on the plane, giving you a precise distance every time. Imagine you're walking up a ramp. Some ramps are gentle, almost flat, while others are steep and hard to climb. Slope is simply a number that tells us how steep a straight line is. It's the amount the line rises vertically for every step you take horizontally, what we call rise over run. Now, if you have two different ramps meeting at a corner, the angle between them is just how much one ramp is tilted compared to the other. In coordinate geometry, we can find that angle just by knowing the slopes of the two lines. So slope is the basic measure of a line's direction, and the angle between lines tells us how those directions relate. In calculus, we're always asking how one quantity changes when another changes, for example, how distance changes with time, which is speed. On a graph, that rate of change shows up as the steepness, or slope, of a line or curve. In fact, the whole idea of a derivative, the core of calculus, is just the slope of a curve at a single point. And when we compare how two different functions change, the angle between their graphs at a meeting point tells us how differently they're behaving. So mastering slope and the angle between lines now is like learning the alphabet before you read. it's the basic language of change that calculus speaks. Let's build this from the ground up. You already know the Cartesian plane and coordinates. Take any 2 points on a line, call them point 1 with coordinates x1, y1, and point 2 with x2, y2. The rise is the change in the vertical direction, y2 minus y1. The run is the change horizontally, x2 minus x1. Slope, which we usually write as the letter m, is just the rise divided by the run. Now, the line makes a certain angle with the positive x-axis. Think of it as the line's tilt. That angle, which we call theta, is connected to the slope by the tangent function from trigonometry. The slope m equals the tangent of theta. So if you know the slope, you can find the tilt angle by using the inverse tangent, or arctan. Let's solve a concrete problem. Suppose you have two lines, the first is y equals 2x plus 1, and the second is y equals negative x plus 3. What is the angle between them? First, identify the slopes. For the first line, the slope m1 is 2. For the second, m2 is negative 1. Now plug these into the angle formula. The numerator is the absolute value of m1 minus m2, which is 2 minus negative 1, giving 3. The denominator is 1 plus m1 times m2, which is 1 plus 2 times negative 1, or 1 minus 2, which is negative 1. The absolute value of 3 divided by negative 1 is 3. So the tangent of the angle phi is 3. To find phi itself, we use the arctan function, phi equals arctan of 3. Using a calculator, arctan 3 is about 71.6 degrees. So the two lines cross at an angle of roughly 71.6 degrees. Imagine you have a line drawn on the Cartesian plane. An equation of that line is just a simple rule, like a secret code, that tells you how the x and y coordinates of every single point on that line are connected. If a point's x and y satisfy the rule, it's on the line; if not, it's somewhere else. So the equation is like a fingerprint for the line. It describes exactly which points belong to it and which don't. For a straight line, this rule always links x and y in a very predictable, steady way. Why do we need an equation for a line? Well, imagine you're tracking a car moving at a constant speed. You know it started at a certain point and its speed, which is its slope. The line's equation lets you predict exactly where the car will be at any future time, without having to plot every single point. In calculus, we study curves, but a curve's steepness at a single point is found by looking at the straight line that just touches it there. So, mastering straight line equations is your first step to understanding how anything changes at a constant rate, which is the very first idea of a derivative. Let's build the equation from what we already know. We know the slope, m, is the rise over run. Now, pick any point on the line and call it x1, y1. Take another general point, x and y. The slope between these 2 points must still be m. So, the rise, y minus y1, over the run, x minus x1, equals m. Multiply both sides by the run, and you get the point slope form, y minus y1 equals m times x minus x1. This is the master key. If you know the slope and where the line crosses the y-axis, that special point is 0, plug that in, and it simplifies to the classic slope-intercept form, y equals mx plus c. Let's solve a real problem. You plant a small tree that's already 5 feet tall. It grows at a constant rate of 2 feet every year. We can model its growth with a straight line. The growth rate, 2 feet per year, is our slope, m. The starting height, 5 feet, is the y-intercept, c, because that's the height at year 0. So the equation is height equals 2 times years plus 5. Now, how tall will the tree be after 3 years? We just plug in 3 for the number of years. That's 2 times 3 plus 5, which is 6 plus 5, giving us 11 feet. The equation lets us predict the height for any year, and the same method works for any situation with a constant rate of change. Imagine 2 ice cream cones stacked tip to tip, forming a double cone. Now picture slicing through this shape with a flat sheet of paper, like a knife. The curve you get on the paper is a conic section. Depending on how you tilt the paper, you get one of 4 shapes. If you slice straight across, parallel to the base, you get a perfect circle. Tilt the paper a little, and the circle stretches into an oval called an ellipse. Tilt it further, so it's parallel to the side of the cone, and you get a U-shaped curve called a parabola. Finally, if you tilt the paper so it cuts through both cones, you get a pair of matching curves called a hyperbola. So, conic sections are simply the family of curves you get by slicing a double cone with a plane. Why do we care about slicing cones? Because these shapes describe how things actually move in the universe. The path of a planet around the Sun is an ellipse. A comet that swings by once and never returns follows a parabola or a hyperbola. When you throw a ball, its path through the air is a parabola. Even the design of telescope mirrors and car headlights uses these shapes to focus light. So, conic sections aren't just abstract geometry, they are the language of orbits, gravity, and optics. For calculus, understanding their shapes and equations is the first step to calculating slopes, areas, and rates of change for these real-world paths. Now, how do we capture these shapes with algebra? On the Cartesian plane we already know, any conic section can be described by a special equation. It's a second-degree equation, meaning the highest power of x or y is 2. The full form looks like ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. The letters a, b, and c are just numbers that control the shape. The magic key is a number called the discriminant, which is b squared minus for ac. If this discriminant is 0, the shape is a parabola. If it's less than 0, it's an ellipse, and a circle is a special ellipse where a equals c and b is 0. If the discriminant is greater than 0, it's a hyperbola. So, by just looking at the numbers a, b, and c, you can tell which conic you have without even drawing it. Let's put this to work with a real example. Suppose you have the equation x squared plus 4y squared equals 4. First, we want to see it in the standard form. We divide everything by 4 to get a 1 on the right side. This gives us x squared over 4 plus y squared over 1 equals 1. Now, compare this to the general equation. Here, a is 1 over 4, b is 0, and c is 1. The discriminant b squared minus for ac is 0 squared minus 4 times 1 over 4 times 1, which is negative 1. Since the discriminant is less than 0, we know it's an ellipse. The numbers under x squared and y squared tell us the size. The semi-axis along x is the square root of 4, which is 2, and along y is the square root of 1, which is 1. A circle is the simplest curved shape. Imagine a point on a piece of paper. Now imagine every other point that is exactly the same distance away from that first point. That collection of points forms a circle. The fixed point is the center, and the fixed distance is the radius. If we place the center at coordinates h and k on the Cartesian plane, and call the radius r, then every point x, y on the circle satisfies the standard equation x minus h squared plus y minus k squared equals r squared. This is just the Pythagorean theorem in disguise. Think of the radius as the hypotenuse of a right triangle whose legs are the horizontal and vertical distances from the center to any point on the circle. In calculus, we study how things change. We often track change along a curved path, like a planet orbiting a star or a car going around a roundabout. The circle is the most basic curved path, so it's our first playground for understanding motion along a curve. A key idea in calculus is the tangent line. A tangent touches a curve at exactly one point without crossing it, and its slope tells us the instant direction of the curve at that point. For a circle, the tangent is always perpendicular to the radius at the point of contact. Mastering tangents to a circle gives us a simple, visual way to grasp the derivative, which is the core concept of calculus. Let's derive the standard equation from the distance formula. The distance between any point x, y, and the center h, k is the square root of x minus h squared plus y minus k squared. For a circle, this distance must equal the radius r. Squaring both sides gives us the standard equation. Now, for a tangent. Pick a point on the circle. Draw the radius from the center to that point. The radius has a certain slope, which is the change in y over the change in x. The tangent line at that point is perpendicular to the radius. So, its slope is the negative reciprocal of the radius's slope. If the radius slope is m, the tangent slope is negative 1 over m. The tangent line's equation can then be written using the point slope form we already know, using the point of tangency and this perpendicular slope. Let's solve a concrete problem. A classic Ferris wheel has a radius of 5 units, and its center is at the origin, so its equation is x squared plus y squared equals 25. Your seat is at the point 3 on the wheel's rim. What is the line of your instant motion as the wheel turns? That's the tangent line. First, find the slope of the radius from the center 0, 0 to 3, 4. The rise is 4 and the run is 3, so the radius slope is 4 over 3. The tangent is perpendicular, so its slope is the negative reciprocal, negative 3 over 4. Now use the point slope form of a line with the point 3, 4, and this slope. We get y minus 4 equals negative 3/4 times x minus 3. This line just grazes the circle at your seat, giving your instant direction of travel. The whole idea is that a circle's tangent is simply a line perpendicular to its radius at the point of contact. A parabola is a special U-shaped curve. Imagine you have a fixed point, called the focus, and a fixed straight line, called the directrix. The parabola is the set of all points that are exactly the same distance from the focus as they are from the directrix. So if you pick any point on the curve, measure its straight line distance to the focus, and then measure its perpendicular distance down to the directrix, those two distances will always be equal. That is the one rule that makes a parabola. Why do we care about the focus and directrix? Because the focus has a superpower, it collects waves. If parallel rays come straight into a parabola, they all bounce off the curve and meet exactly at the focus. That is why satellite dishes are shaped like a parabola, to gather weak signals from space onto a receiver at the focus. A car headlight does the opposite, it puts a bulb at the focus, and the mirror bounces the light out in a straight, powerful beam. And the tangent line, which just grazes the curve at one point, is the key to understanding how that reflection works. It is the line that acts like a flat mirror at that exact spot. Let's build the equation from the ground up. Put the focus at the point 0, or on the y-axis, and the directrix as the horizontal line y equals negative a. Now take any point x, y on the parabola. The distance to the focus is the square root of x squared plus y minus a squared. The distance to the directrix is just the vertical distance, which is y plus a. Set them equal, square both sides to get rid of the square root, and expand. The y squared and a squared terms cancel out beautifully, leaving you with x squared equals for ay. That is the standard equation. The number for is the key, it tells you how wide or narrow the bowl is. For a tangent, we borrow an idea from calculus. The slope at a point is the derivative, which for x squared equals for ay works out to x over 2a. Let's solve a concrete problem. A solar cooker uses a parabolic mirror with the equation y equals 8x squared. We need to find the focus to place the cooking pot. First, rewrite the equation to match our standard form. Divide both sides by 8 to get x squared equals 1/8 y. Now compare this with x squared equals for a y. We see that for a must equal 1/8. So a is 1/8 divided by 4, which is 1/32. The focus is at 0, a, so it sits at 0, 1/32 units up from the vertex. That is where the sunlight concentrates, and where you put your pot to boil water. The whole idea is, a parabola is just a set of points obeying a simple distance rule, and that rule gives it the power to focus energy. You already know that slicing a cone gives us circles and parabolas. Now imagine tilting that slice just a little more. If you cut through the cone at a gentle slant, not steep enough to make a parabola, you get a closed, squashed loop, that is an ellipse. It looks like a circle someone sat on. If you tilt the slice even further, so it cuts through both halves of the double cone, you get two separate, mirror image open curves flying off in opposite directions. That is a hyperbola. So an ellipse is a stretched circle, and a hyperbola is a pair of outward opening arms. Both are conic sections, just like the circle and parabola you already met. Why do we care about these shapes? Because the universe is full of them. A planet like Earth doesn't travel in a perfect circle around the Sun, its path is an ellipse, with the Sun sitting at one special point called a focus. A comet that swings past the Sun once and never returns traces a hyperbola. To understand motion, orbits, and even how light bounces inside a mirrored room, you need ellipses and hyperbolas. In your calculus course, you will find slopes of tangents to these curves and compute areas under them. So learning their basic equations now is like learning the rules of the road before you start driving. Let's build these curves from a simple rule. Take two fixed points, called foci. For an ellipse, pick any point on the curve. The distance from that point to the first focus, plus the distance to the second focus, is always the same total. Imagine tying a loose string to two thumbtacks on a board. Pull the string tight with a pencil and trace around, you get an ellipse. For a hyperbola, the rule flips, the difference of the distances to the two foci is constant. It is like a sonic boom, a point on the curve is always a fixed amount further from one focus than the other. From these distance rules, we can derive the standard equations. For an ellipse centered at the origin, with its widest span A along the x-axis and tallest span B along the y-axis, the equation is x squared over a squared plus y squared over b squared equals 1. Let's solve a concrete problem. Imagine you are in a whispering gallery, an elliptical room where a whisper at one focus can be heard clearly at the other focus. The room is 6 meters tall at its center, and the distance from the center to one focus is 4 meters. What is the width of the room? We know the height gives us the semi-minor axis of B as half of 6, so B equals 3 meters. The distance from center to a focus is called C, so C equals 4 meters. For an ellipse, these are related by C squared equals A squared minus B squared. Plugging in, for squared equals A squared minus 3 squared, so 16 equals A squared minus 9. That gives A squared equals 25, so A equals 5 meters. The full width of the room is the major axis, which is 2A, so 2 times 5 equals 10 meters.